All right, so we're happy to have Charles Bédard present to our group his research on the Deutsch Hayden descriptors and factory and entanglement. Please tell us about your work.
Thank you, Mark. Pleasure to be here. Yeah, so Deutsch, well, it's good because Hayden was a supervisor of Mark, and when I discussed with Mark, he was keen to know more about work from his previous supervisor. So that's, in fact, what I'm going to be doing here is essentially presenting you. Um, it was written in 1999, published in 2000, so it's a rather old paper by Deutsch and Hayden, but it kind of went under the radar, at least in my opinion, especially in contrast with the claims it makes, right? So I guess if you read the title I've put forth, um, well, that might quickly fall into the crackpot category. Like factoring entanglement seems like a contradiction in terms. Um, and indeed, if we look at things as we're usually taught in quantum theory, a system AB is entangled if, by definition, its wave function psi of AB cannot be factored, right? It doesn't admit this decomposition into tensor products. So, right, yeah, as I said, factoring entanglement appears like a contradiction in term. Now, quick question: do you guys see the upper right corner where my
I
mouse
do.
is?
Yeah,
Okay.
I didn't realize there were so many symbols for contradiction, so that's
Yeah,
nice to learn.
me too. Same here. Right. So let me be a bit more precise about like setting the stage, if you will. Let us consider a very basic scenario where Alice and Bob share a pair of particles in the state phi plus 0, 0 plus 1, 1. Now, I'm interested in how can they describe their own particle in and of themselves, right? So Alice has a particle. Of course, we know it's entangled, the whole wave function is unfactorizable. Yeah, but what can we say about Alice's own particle? And well, there's obviously, I'm sure you guys have heard about reduced density matrices. Is probably the description that comes to mind, right? So Alice can describe her particle with a 2 by 2 matrix. In this case, it would be proportional to the identity because, well, if you trace out Bob's system here from that wave function, that's what you get. And similarly, Bob can describe his particle with his reduced density matrix. And that mode of description is local. In which sense? And I'm using the criterion of Einstein, that Einstein coined. The description of system A is independent of what is done with system B, which is spatially separated from the former. So that means that whatever Bob does to his system, he applies a gate, he measures it, he eats it, I don't really care. Whatever he does to his particle, it will leave invariant Alice's description rho A. All right, this is well known from the no signaling theorem. And so that's the sense in which I declare that this mode of description is local. However, it's not complete. Why? So the mode of description of reduced density matrices is not complete because we cannot compute the distributions of all joint measurements that would eventually be performed on the pair of systems from the local descriptions of A and the local description of B, right? This is also well known. If you have row A and row B, you've traced out too much information. In particular here, I can no longer recover phi plus. In fact, each of the four Bell state would lead to the same reduced local densities. And so if I were to rejoin the system together physically and perform a joint measurement in a Bell basis, well, I could not predict the correct distribution of outcomes from row A and row B. Right? So this distribution of measurements on a joint system is usually given by the global density matrix, which here is ket phi plus bra phi plus. But that is, just to repeat myself, it's unobtainable from row A and row B alone. And so, okay, so that's one way in which Alice and Bob can choose to locally describe their particles, but we can make another choice, right? If we want to circumvent the second difficulty, namely the completeness issue, we can say, you know what? Alice will describe her own particle with the global state phi plus, and Bob will do the same thing. In this way, as I said, we circumvent this because now we have a complete description. We can obtain the global description from collecting the local parts, like trivially, basically, because I'm embedding the global description within each local system. However, we no longer have a locality. Why? Because if Bob happens to play with his system, old school notation for the X gate, right? The NOT gate. He will affect his own system and his own description of his system, which is so far fine, no problem, because Bob is acting on his system, so he can change it. However, we've declared in this view that Alice was also describing her particle by the global state. And so Alice's description also must be updated and updated instantaneously. So whenever the global state changes, the global state changes also for Alice. But no action was performed on Alice's system, right? So in this sense, it would not fulfill Einstein's criterion of locality. So at least when I started graduate school, I made peace with this form of dichotomy. I thought like, yeah, that's what quantum theory is like, right? Mm. And I think many colleagues are also in that situation. We end up making peace with it. And we're kind of telling ourselves that descriptions of entangled quantum systems can either be local or complete. And we're going to kind of usefully choose whichever framework for whichever problem we're interested in. But that dichotomy has been proven false by Deutsch and Hayden in 2000. And that's the point of my presentation today. They exhibited a mode of description, a way to describe quantum systems that is both local in Einstein's sense and complete, namely that you can just join the descriptions together and reobtain the global density operator, or if you want, be able to predict all distributions of measurements performed on the joint system. Right. So to go back to my little drawing here, it means that Alice has a mathematical object QA. It's called QA. Bob has QB, and it's called a descriptor. The descriptor of Alice is QA. The descriptor of Bob is QB. If Bob plays with his system, it will affect QB. So QB might evolve to QB prime, but it will leave QA invariant. And moreover, if you're given QA and QB, well, you can compute from that the global density operator, phi plus, phi plus. Okay, so that's what it means. It's local and complete. We have basically whatever we like from the locality of reduced densities, but we have whatever we like from it contains all the information of the global state. Some people in the literature might also say that instead of speaking of locality and completeness, we might also say that the mode of descriptions satisfies local action, and moreover, it's separable. So separable is this idea whereby if you want to describe the whole, you just need to describe the parts, right? So a valid descriptor for the pair of particles would simply be the collection of local descriptors, QA, comma, QB, and then you have a descriptor for the whole. That's a separable description, and we have it with descriptors. Okay. By the way, I'm all in for. I'm obviously happy if you have clarifying questions during the talk. So far, so good, or
Yeah, we're good.
Okay.
We're certainly here and listening very intently.
Good to know.
Since it's being recorded, we don't necessarily want to interrupt too much, but yeah, as you progress, we'll interrupt if we need to clarify.
Yes, yes, please. Yeah, there's obviously the kind of questions that are worth discussing at length afterwards, but sometimes a little clarifying question right in the middle can make a difference. Please don't hesitate.
Sure.
Okay, cool. So, right, factoring entanglement, then, as I've promised here so far, I haven't explained much. I just told you about it. It makes sense in the Deutsch Hayden framework. And my goal is basically to give you a crash course on how it works. Okay, because I guess the context behind this talk that I've put forth is because I was giving many talks about which kind of problems this framework can solve. And then every time people were telling me, oh yeah, but like, are you kidding? Can you really do that with, is there really a description of quantum systems that is kind of factorizable? How does it work mathematically, right? So this is really like it could have been like a Blackboard talk where I take you for 2 hours on, yeah, here's the mathematics behind it. I hope it interests you in case you want to know like some other aspects, like which kind of problem can it solve on the questions of locality, then either re-invite me or check out on YouTube. I've got some talks or obviously the papers. Okay, so it's
We'll consider inviting you again.
yeah, why not? Perfect. I've published that in Quantum Reports. So it was an appendix of my PhD thesis that I wrote basically for my examiners to understand the framework. And Lev Weidman at some point came after me and said, well, are you going to publish that? Because I read this appendix and it was very clarifying for me. Now I can understand the Deutsch Hayden framework. And so he invited me to publish in the journal of which he's the academic editor. So it was published under the title, The ABC of Deutsch Hayden Descriptors. It's really like, you know, basically like a textbook presentation of how it works. And that's what I'm doing today. Right? But really what I'm telling you about is this paper, Information Flow in Entangled Quantum Systems. So one aspect of it is that I felt like it was cited something like less than 300 times. And for a paper with these claims, especially in the foundations of physics, I think it went undercited. So one aspect of the Deutsch and Hayden paper is that it's not an easy read. You don't go on the first pass and go like, oh yeah, obviously. No, so I worked hard on it, and this is kind of my best pedagogical take on it. Good. As I mentioned, there are problems to be solved with the framework, notably teleportation, superdense coding, Bell, and quantum causal models. I can briefly comment on that afterwards, but really the main goal today is to tell you about how it works. So the Deutsch Hayden formalism is essentially quantum computation in the Heisenberg picture, right? It is, by the way, very much connected to Gottesman's 1998 Heisenberg representation of quantum computers. And that is basically just doing quantum information and quantum computation in the way in which quantum mechanics was discovered 100 years ago by Heisenberg, with matrices evolving in time. And these matrices are observables evolving in time. And the things we call states and the kets, they stay static. That's the Heisenberg picture. So yeah, one quick comment is that what I'm telling you about is not about interpretation. We could discuss interpretation afterwards if you're interested, but prima facie, the talk I'm giving is really just a mathematical framework for quantum mechanics, but Heisenberg way. Okay. Calculations in quantum theory take this form, right? We have this object, a bra, and that object, which is a ket, and in the middle, we've got some stuff, usually a unitary operator and an observable. And this kind of calculation, we may say, at least in physics, it's the expectation value of some observable, right? So this is a state, that is the unitary evolution, and that is an observable, as I said. Okay, in the language of quantum information, sometimes people are a bit less familiar with observables. In physics, it's quite routine, a Hermitian operator. Uh, but I mean, yeah, that would be more like the classic setup in quantum information where we make a measurement in the computational basis. But all calculations that we do in this traditional setup of quantum computation is a special case of actually measuring the expectation value of an observable, as we'll see shortly. So for example, here we prepare a state in this in the state ket 0, which we could take as an eigenstate up of a spin operator if you want, or I will remain abstract with the ket 0, ket 1 notation. And then we find a unitary operator u between time 0 and time t. And to compute the state at time t, we act u acts on ket 0, and it gives us, for example, psi of t. Psi of t would be here represented in the computation. And now, yeah, for example, psi of t may be alpha 0 plus beta 1. And if we measure, we know the drill, we get 0 with probability norm of alpha squared and 1 with probability norm of beta squared. And where I'm saying that this kind of calculation with an observable that is being sandwiched by psi of t crops up when we want to make sense of this alpha squared here. Why? Because what we're basically doing is that this alpha squared comes from a specific kind of calculation like that, like a sandwich-like calculation where this is a bra and this is a ket, where it's like the bread of my sandwich. And in the middle, what do I put? I put the projector onto 0. Right? So I'm sure you've seen that before. This is just to justify the fact that if we, even those of us who use the Born rule kind of quickly and saying, oh, it's that number squared to get the probability here. Well, yes, okay, but that number squared is also a special case of this kind of calculation, all to justify that in the kind of calculations we make in quantum theory take this form. All right. What we've been doing here, though, is everything's happening in the Schrödinger picture, where the state evolves in time. The unitary operators are being acted on the states. Now, when we move to the Heisenberg representation, that's what's going on. The unitary operators are acting on the observables to make the observable evolve in time, while the state remains constant and fixed. So actually in the Heisenberg picture, it's helpful to speak of an initial observable, which might be that O in the middle. I could explicitly write it at O of 0. It's the observable at time 0. And when we conjugate it by the unitary operators, then we've evolved it to O of t, observable at time t. Now, here's a question for the Heisenberg picture. Does one need to keep a table of all evolutions of all observables, right? Because one strength of the Schrödinger picture is that we were following in time our beloved psi of t, and we did not know in advance, we did not need to know in advance which observable or which projector we were caring to measure. Whenever measurement would happen in some basis, we had the mathematical tool, namely psi of t, to answer the question. However, with observables, we might wonder, yeah, but which one should we track in time? Because it might not be clear in advance which observable we're going to care to measure. Maybe we're going to measure in a different basis than the computational basis. Maybe we're going to measure, as physicists do sometimes, some observable, which is usually written with an eigendecompositions of various eigenvalues, right? And if it happens that we had not tracked in time that specific observable as a description of the system, well, then how can we answer? And so prima facie, to have a valid Heisenberg description, we would need a table of the evolution of all observables in time. But the bad news is that that table is not only infinite, it's uncountable. There's uncountably many observables to track in time. So, well, the answer is no, we don't need to track all observables. And in solving that question, we basically get to the Deutsch Hayden framework. So let's focus on it. What do we need to track in time if we want to be able to answer to well, if we want to be able to predict or to compute, should I say, the expectation value of all time-evolved observables. First thing to realize is that a basis of operators suffices. So why? So the BIs would be an operator basis, right? And any observable at time 0, by virtue of BIs being a basis, could be expanded as a linear expansion of AI BIs. Okay? And if I know how the BIs of 0 evolve in time to BI of t, then I know also how this observable would evolve in time by linearity, right? Because if I want to now compute O of t from the BIs of t, well, O of t is by definition the conjugation by U of O of 0, and that can be expressed like this. And that is the sum over AI BI of t. Okay, so just to repeat it quickly, because it's kind of important, I'm assuming here I know how BI of 0 evolves to BI of t for all basis elements of my operators, operator basis. Then I'm eventually asked, okay, Charles, please give me O of t for some generic O, like observable at time 0 that we know the prescription. It's written by this sum of AI BI of 0. Well, the answer is, okay, sum of AI BI of t. I use the information of how my basis operators evolve to compute the time-evolved observable. Right. Now let us focus on one qubit. The whole universe is made of one qubit. A canonical basis, or a useful basis, I should say, of operators to track in time when we speak of a qubit is that basis. Identity, poly x, poly y, poly z. It does form a basis, and more specifically, in fact, it forms a basis of matrices, 2x2 matrices, if I take complex linear combination, and it forms a basis of Hermitian matrices if I take just real linear combinations. That's a fun fact. It's not fundamental for the discussion, but in fact, what matters most for our purposes is that really that we could take complex linear combinations and get to any matrix 2x2. Now let me give those a name. This will be Qi of 0, Qx of 0, Qy of 0, and Qz of 0. And I will embed these 4 matrices into a 4-tuple, quadruple. Okay, and that is the descriptor of my system at time 0. Right? Because what I want to track in time in the Deutsch Hayden picture is a set of operators that are evolving in time, which enable me to then reconstruct all time evolved observable. And as we've seen here, a basis suffices. But we'll see that we can be more economical than tracking these 4 operators. Right? Now, the evolution of the descriptor is given by this, right? Like all operators in the Heisenberg picture, in fact, these are even observables, so they evolve with the conjugation by U. So the descriptor at time t would be that quadruple. You simply conjugate by U each entry of your quadruple. I remind you that these entries are 2x2 matrices. These unitary operators, because I have a 1-qubit universe, are 2x2 matrices as well. The whole thing makes sense. Now, please observe that the identity evolves trivially. Namely, it just doesn't evolve. So tracking in time the identity is really just a waste because it's always going to be the identity. So let's drop this one. Moreover, there's another redundancy that we can exploit. Qy of t, for example, is, as I said, is U dagger Qy of 0 U. But Qy of 0 can be expressed as a product of Qx of 0 and Qz of 0. Right? That's just the algebra of Pauli operators. It's cyclic. So that equation holds. But then I can reinsert the identity in the middle with U and U dagger. And I realize that what I've just wrote down here is nothing but I qx of t qz of t. Therefore, since at time 0 I can generate sigma y with a product of sigma x and sigma z, it means that the descriptor also at time t of y is nothing but the same product of the descriptor of x at time t and the descriptor of z at time t. And therefore, I can also dismiss tracking in time the y component because it's basically redundant. You know, this matrix Qx of 0, which is this Pauli X matrix, will evolve to some other matrix generically, Qx of t. Qz will evolve to another matrix, Qz of t. Now you can say, well, Qy would also evolve to another matrix, so I'm going to track that in time. But no, because you get with Qx and Qz, you have all what you need to recompute Qy via I Qx of t, Qz of t. And so there's no need to track Qy of t in time. Therefore, the descriptor of a single qubit is in fact a pair of operator, Qx of t, Qz of t. And I may refer to the x component of my descriptor, you know, Q of t. It's bold font, right? Because it's a tuple. It's a vector, if you want. It has two components. And whenever I zoom in into a single component, it's no longer bold font, right? But if I take this bold font object and I speak of its x component, it's just a way to mean its first component, which is that operator, which at time t may no longer have the form of the Pauli X matrix because it's been conjugated by some unitary operator, so it might have lost this form, right? And if I speak of the z component of the descriptor, I'm implicitly referring to the second entry of the pair, which is Qz of t here. So far, so good?
Yes.
Excellent. Right, descriptor of the qubit. So I guess mathematically speaking, what is a descriptor? It's not really a basis anymore because we've managed to reduce it even more, distill it even more. It's a generating set of operators acting on C2, right? At time 0, it's easier to think of it at time 0. A generating set means you can first multiply these objects together to then get an operator basis. And since you have an operator basis, then after with linear combination, you can get to any operator, right? So you can generate any operator via multiplication and addition. Okay, so in the Heisenberg picture, if we're to describe our systems, system at time 0 will be described by Qx of 0, Qz of 0, and at time t, Qx of t, comma, Qz of t. Let's do an example just to make sure we're all grasping the idea. That's the setup. We prepare a qubit in the state 0, we apply a Hadamard gate, and we measure. All right, I've labeled the times, time 0 and time 1. Like the most simple example of quantum information. Now, the Hadamard gate is given by this here, this expression, this matrix. And how to describe the system at time 1? That's my first question. I want to describe my system at time 1. And what's the probability of measuring outcome 1? My second question. Quickly, in the Schrödinger picture, it's a trivial problem where we all know how to do that. That's a description of my system at time 1. And if I measure, I obtain outcome 1 with probability 1/2, that number squared. Good. As I promised, you know, like this 1/2 comes from a calculation like that, which, in fact, in this case, if we unpack it, this is the calculation we're doing. All right, the observable in this case, observable is a Hermitian operator. Guess what? Projector onto state 1 is also a Hermitian operator, so that's a specific kind of observable. Hadamard would be my unitary operator in this case, and ket 0 is my initial state. But in the Schrödinger picture, that's what we do when we do the calculation. We get the Hadamars to act here, we get a plus, and we do the calculation and get, yeah, 1/2. Now in the Heisenberg picture, well, the whole point of the example is not to do it in the Schrödinger picture, but rather in the Heisenberg picture. How to describe the system at time 1? And what's the probability of measuring outcome 1? Okay, so we're going to get to a calculation like that eventually to answer the second question, right? But we're going to be wanting to act in the middle. But let's go first to the first question. How do we describe the system at time 1? So remember that the descriptor at time 0 was given by the pair of operators sigma x and sigma z. So we find that that is the description of the system in the Deutsch Hayden framework at time 0. What is it at time 1? Well, we sandwich these descriptors with the Hadamard gate. And note here for conciseness, I can drop the of 0. If you see a QX without a time label, implicitly I'm thinking about it at time 0. And so, right, so this is what I mean by this expression. Right? When you conjugate this tuple, you mean you conjugate it pairwise. And most of you, I'm sure, know the sigma x that is conjugated by a Hadamard gate gives you a sigma z, and the sigma z that is conjugated by Hadamard gives you a sigma x. Re-expressing that in terms of q simply means just qz comma qx. And so my descriptor at time 1 is qz at time 0, comma qx at time 0. Right? So if I was describing my system like this at time 0, now I'm describing it like that at time 1. It seems like what the Hadamard gate does is to swap the descriptor components. But now, what's the probability of measuring outcome 1? I still want to answer the question within the Heisenberg picture philosophy, right? So I'm not going to redo all the calculations in the Schrödinger picture. And the trick is to realize that, well, that's a specific kind of matrix. As we've seen, it's a specific kind of observable. And we argued that at time 0, these two operators had the generating set ability. They were able to generate any operator by multiplication and then addition. So the game now is to try to get this matrix as a function of these two operators. Okay? So that matrix is nothing but this matrix, in fact, which you can rewrite as 1/2 the identity minus sigma z. And so it's the identity minus qz of 0 divided by 2. Okay, so what I've done here is to find an expression in terms of my descriptor components at time 0, which are the sigma x matrix and the sigma z matrix, and perhaps the identity, because I get the identity for free. And if I need sigma y in my expression, I would have simply multiplied qx and qz together to get sigma y. And that's the solution. So I'm going to go back to this calculation here, and I'll insert what I found, which is an expression in terms of the descriptor components at time 0. So when I say descriptor components, because if I say just descriptor, I have in mind this bold font object, which contains two operators. Descriptor components would be either qx or qz here at time 0. And then what I've done in this second line is I've realized, oh, that's my unitary operator that's acting on the operators in the middle. And what it did is that it transformed my operators at time 0 in terms of operators at time 1. And therefore, I've taken the same expression that I had, namely identity minus qz at time 0 over 2, but I've now expressed it at time 1. Identity minus qz at time 1 over 2. And I distribute the Heisenberg state, which is this constant kit 0. And then that singles out the upper left matrix element of the matrix. So that will be a 1 and that will be a 0. Divided by 2, 1/2. Okay, so of course you might say, oh, I would have done that calculation differently. Like there's obviously many ways to do this calculation, but I'm walking you one specific way to do the calculation to slowly get you to think about how descriptors work and how we'll be using them, right? So this question of what's the probability of measuring outcome 1, we know is that calculation, but what I've done here is I've exhibited how to leverage our descriptors at time 0, descriptors at time 1 to get the answer we want. Okay. 1 qubit. I said at time 0, at time t, and between the two, it has some unitary operator u in general. Now let us zoom in a little bit more on that. And let us assume that u is in fact, you first do v between time 0 and time t minus 1. Then you do w between time t minus 1 and time t. Okay? Why not? Some quantum computational network may look like that, obviously. So you all know that u is, when we want to write it, we have to make a little twist here. We do v from the right and then w, right? Because this v is supposed to act on a state, so v acts first and then w. And the u dagger would be v dagger, w dagger. What's the problem now? I've told you that the descriptor at time t is given by this expression. U dagger, descriptor at time 0, u. Fine. Let's substitute u dagger and u with these w and v. That's what we find. Right? U dagger is v dagger, w dagger, and u is wv. And so what we're doing here is we're evolving the descriptor at time 0 first by acting with w, which is the last gate of the circuit. I hope you see this is a problem. Like, how can it even make sense, right? You have your descriptor at time 0. It's like freshly prepared, right? Q of 0. Now I want to evolve it. I'm going to start with the last gate. Why on earth would you do that? Like, how does it physically make sense, first? And second, how is it even useful for computation? Like sometimes you want to evolve your state, but you don't yet know what will be your last gate. You'd like something that will enable you to evolve it like from time 1 to time 2, and then time 2 to time 3, and then you don't need to know what's the last gate before starting computing anything. So that's the problem that we face now. I call this problem evolution from the future ? It looks like we're evolving things from the future. If we want this framework to be any useful, we have to solve that. So the trick in solving this is to realize that not only descriptors generate operators that we understood them as observables, but they also generate evolution operators. Because evolution operators are also, in the case of 1 qubit, 2 by 2 matrices. And our sigma x and sigma z that we've found had the ability, if we take complex linear combination, to generate any matrix, not just observables, right? You multiply them, you get sigma y. You also have the identity for free, or if you don't like my argument that you get the identity for free, you get the identity from qx times qx. That's the identity. And then you have complex linear combination, so you can get to any matrix, and therefore you can get to any unitary matrix, which are evolution operators. Right? This was my argument to tell you that that specific matrix it was possible to generate it with descriptor components via this prescription here. But now we could do the same drill with a gate, with a unitary gate like the Hadamard. We can play the same game. That's a matrix. Let's see, mathematical puzzle, how to generate this with sigma x and sigma z. Okay, so we play the game. We rewrite this matrix as 1 over root 2 the off-diagonal elements plus the diagonal elements. And right away, the solution is in our face. It's 1 over root 2 sigma x, which is the descriptor of x, the x component of the descriptor at time 0, plus sigma z. What do we do with this? So, right, this permits us to define the functional representation of the gate H via this U sub H of something that has two arguments is called the functional representation of the gate H. And in solving this puzzle of how to express the matrix representation of H as a function of the descriptor component, I am finding the functional representation of H. So in this case, it's 1 over root 2 first argument, qx of 0, plus 1 over root 2 second argument, qz of 0. Right? So I insist that, I'm sure you guys know that, but when we speak of a function, we don't really care anymore about the arguments themselves. So if I would do functional representation of H of blue square and red triangle, well, the solution is 1 over root 2 blue square plus red triangle. That is the functional representation of H. I insist on that aspect because we might eventually be interested in the functional representation of H expressed in terms of the descriptor components at time t. Well, then what that is this again. Okay, so what's the deal in the Heisenberg picture? The deal is that the functional representation of gates is fixed once and for all. In the case of the Hadamard, that's the functional representation of the Hadamard gate. However, if I express, if I calculate the functional representation in terms of time evolving descriptors, like at time 0 and then at time t, well, the overall matrix that it will produce will change in time, obviously, because my arguments change in time. But the function itself is fixed. It turns out that in general, we won't be interested so much in, okay, but then what's the overall matrix of that? That will not be so much interesting because we're going to be working algebraically with the algebraic properties of qx of t and qz of t instead of working like with the matrix calculus. Okay, so I did the example for the Hadamard gate, right? But it works for everything. It works for any gate. Any gate W is, by virtue of being a 2x2 matrix, is a linear expansion in that basis at time 0. And now, yeah, as I said before, if you like the identity, I get it for free, or I get it in particular because it's qx squared. And why I don't need it, because of this argument where I can generate it as I qx of 0, qz of 0. And therefore, this expression here defines the functional representation of the gate W. Okay. And right. Now I'm going to do something silly. I'm going to say, let us suppose that we have a unitary operator V that represents the dynamics between time 0 and time t minus 1. And I'm going to compute, just for fun, V dagger W V. Why not? Just for fun. All right, so I'm computing this, V dagger and V on each side. Well, it's clear from this first line what the solution will be, because the V dagger and V will go on in each term, and each term here will have its operator. For example, in this case of that term, we have qx of 0. That operator will now be sandwiched by V dagger and V. And therefore, the qx of 0 will evolve to qx of t minus 1. Same with y, same with z. And therefore, and notice that the expression will not have changed. So whatever was the functional representation at time 0 that we found for W If I sandwich it by V dagger and V, I can basically get the V's inside the expression. And therefore it's the same functional representation, UW of V, pardon me, UW, but expressed in terms of Q of T minus 1. Okay, it was clear from this line. If you want, it's also clear here, but you may have to reinsert V dagger V here in the middle to accommodate the fact that these operators need to evolve in time. Okay. Okay, so I just said we find the functional representation of some gate W, and we might for some reason be interested in time evolving the gate itself by V. Now, it happens to be very helpful in this case, right? We were worried about this insanity where the descriptor at time 0 was first evolving by the last gate. But here's the trick. Insert VV dagger in the middle. VV dagger in the middle. Okay? And I'll remind you that V dagger Q of 0 V was Q of T minus 1, right? Because that's the unitary operator between 0, time 0, and time T minus 1. Therefore, I've evolved my descriptor until time T minus 1. So that will give me this part, the middle part of the equation, I can replace by Q of T minus 1. And I'll remind you what we just computed with this calculation we just did, which was V dagger WV. Well, it was the functional representation of the gate W expressed in terms of the descriptor at time T minus 1. So we've got all the ingredients to rewrite this line as that. Okay, what is it good for? Is that now we've derived another formula for the evolution of the descriptor at time t, but that formula is expressed in terms of the descriptor at time t minus 1, and in terms of the gate that is being applied between time t minus 1 and time t, namely w in our case. So although we had this other formula, which is basically this one, that relates the descriptor at time 0 and at time t by one big application of a gate, we can also, which was this one also, right? So Q of t is U dagger Q of 0 U. We can also decompose it incrementally and re-express the evolution in a step-by-step fashion. And it turns out that this will be useful. Why will it be useful? There's another problem I kept under the carpet, is that when we computed this example of, we have an initially prepared descriptor and we apply the Hadamard gate, we found that expression, QZ, QX. So I said we switched the descriptor component. But our calculation was done with the matrix calculus. I use the identities that I'm sure you guys know well, that when you sandwich a X, poly X by a Hadamard, you get a poly Z. But it turns out that in the Deutsch Hayden framework, we do not want to do calculations this way, because that's of a too narrow scope. Because if we do calculations this way, we can only answer what's going on between time 0 and time 1. Here's another way to do the calculation. Right, this is what we found, right? And the problem is, what if, in fact, we would have had the descriptor at time t minus 1, which by definition has two components, so the x component of the descriptor at time t minus 1. Now this object is no longer a sigma x matrix, and QZ at time t minus 1, right? How can I be sure that the Hadamard gate really does swap the entries? Because this kind of calculation won't work. Because basically I can no longer sandwich the matrix representation of H. And so what's going on in this case? Let's redo the thing between time 0 and 1, but we'll redo it algebraically. Okay, so I came back to time 0 and time 1. I want to re-verify this. But what we'll be doing is that we're going to be using our step-by-step equation of motion, if you want, which we just derived, right? Which was this one here. The descriptor at time t is related to the previous descriptor at time t minus 1 via this sandwich calculation where this uw is the functional representation of the gate w. Now we had computed together the functional representation of the gate h, the Hadamard gate. Its functional representation is given by this. And so using these formulas, I arrive at that, right? Oh, and by the way, now I'm going to compute it, not the two of them together like I did here, but I'm going to compute it one at a time. So let's just focus on the x component of the descriptor at time 1, which is qx of 1. And that's why it no longer is bold font. It's only one component, one operator. It's not a tuple anymore. Okay, by this formula, what I need to do is to take my descriptor, the x component of the descriptor at time 0, and sandwich it with the functional representation of the gate h expressed in terms of the descriptor at time 0. Right? You're substituting 0 by t minus 1 in that expression. And so 1 by t. And then on the second line, I use the fact that we found that the functional representation of the gate h was 1 over root 2 qx plus qz. Note that here I've dropped the parentheses of 0. I've dropped the dependency on time 0 because it would just make the equation heavier. Okay, so that is how I want to compute the evolution of the first component of the descriptor. And we do the calculus with the algebra. So I distribute each term. I end up with 4 terms, all of this kind. And now I need to basically know the algebra of descriptors, which is the same way as saying the algebra of the Pauli operators, right? The Pauli operators are such that if you multiply 2 Pauli operators together, you get the identity. And they're such that if you multiply x and y together, you get iz, and same for all cyclic permutation. And so from that, you get that the descriptors anti-commute, or that the Pauli operators, sorry, anti-commute. Why? Because take the dagger on each side of the equation. If you take the dagger on each side of the equation, Pauli matrices are self-adjoint. So taking the dagger won't harm, except that it will change the order. And when you change the order, the I will become a minus I. So that's why one way to see that they anti-commute. I'm using those two properties to carry out the calculation here. When I find 2 qx's together, I can reduce them to the identity. So qx cancels out, qx cancels out, like that. And then here, I'm going to use the fact that qz and qx anti-commute. So I pick up a minus sign. And then qz meets qz and cancels out into the identity. So I'm left with this here. My qx's cancel out, and my qz lives. So, and that was at time 0, right? All the time labels were dropped, but what we've computed at the end of the day, and we've computed with the step-by-step equation of motion and with the algebra of descriptors this time, we've computed that the first component of the descriptor at time 1, that is the x component of the descriptor at time 1, is equal to the second component of the descriptor at time 0. But Charles, we already knew that. We've computed it before. Why are we doing this again? Because now we can easily solve for generic time, right? At a generic time, I'm doing my Hadamard gate between time t minus 1 and time t. And my input descriptor, if you want, is given by this. Qx at time t minus 1, qz at time t minus 1. Well, this calculation carries through, whereas that one did not carry through. So
I have a comment.
Yes.
With this calculation that you showed, in the second to last step, there's a kind of quantum interference that occurs, right?
Yes.
Like the operators cancel out. So usually we think about quantum interference with probability amplitudes, but now we're seeing it here in this Heisenberg picture with operators. So that seems interesting.
Yes, nice comment. I agree. Yes.
Actually,
So
we're hitting an hour. Would you mind if we took a short break?
sure, no problem.
I'll
Up
do
to you.
pause
Like
recording.
so I didn't rush. I'm free. I can continue after the break if you want. I
Okay,
can
yeah, yeah.
also.
Yeah, I'm very curious to see the Bell inequality, actually,
Ah, okay. You
like teleportation and superdense coding.
okay, good. Okay, well then we'll have a little
Puzzle
program
models.
together then, because in this talk, as I said, I'm basically setting up the math right.
Yeah,
Um, to do the to do the teleportation protocol, it's better if you know the formalism. Otherwise,
right.
I managed to find a way to give a talk to people who did not delve into the math of Deutsch Hayden, but they have to take my word for it. Like, oh, that's how things work in the Deutsch Hayden picture. Okay, yeah. So it's a bit boring, but I think this we're doing things correctly. So if it interests you, I'll be able to come again.
Yeah. Let me do a pause recording. We'll come back in like 2 or 3 minutes.
Perfect.
Go ahead.
All right, so I just claimed that this calculation carries through between time t minus 1 and time t, but why precisely? Right, the calculation we've made here leveraged the algebra of descriptors. Notably, this equation that if you multiply two descriptor components together, you get the identity and the fact that they anti-commute. But that was descriptors at time 0. What about descriptor at time t or time t minus 1? Well, we have to realize that this algebra of descriptors is preserved in time. So if that equation held at time 0, it also holds at time t. Why? Not yet. And if that equation holds at time t, at time 0, it also holds at time t. Why? That's why. It's a few lines, you can verify it, but you express it at time t, and then you cancel out the operators in the middle, you use the algebraic relation at time 0, and you recancel out the operators. And here it's a similar trick. So the algebra is preserved in time, right? So I could use the same algebraic relations with my descriptor components, but expressed at time t. Or in my case, at time t minus 1, I will be using them, right? Because now the calculation I want to do is to find what is the first component of the descriptor at time t. And I have a step-by-step equation which prescribes me operators in terms of time t minus 1, right? Here, note that here I'm kind of using a trick. I'm saying, oh, I also dropped the time labels. And earlier these dropping the time labels was just a way for me not to avoid writing at time 0 in each of the operator. But now what it means is it's at time t minus 1. Okay, so I've dropped the time labels, but each of these q's are in fact q's at time t minus 1. However, the rest of the calculation was just leveraging the algebraic properties of these operators, and these algebraic properties carry through. And this is why we can say that the descriptor at time t, well, at least we've computed the first component, will be the z component of the previous descriptor. And if we would have calculated, z here, we would have gotten x here, and therefore we can safely claim that the Hadamard gate switches the descriptor component when the descriptor enters the Hadamard gate. And it does so regardless of its matrix representation when it's being applied. Okay. Now I'll be moving to n qubits, because so far we considered just a 1-qubit. Not only we consider 1-qubit, we consider 1-qubit universe. There's nothing else to describe than 1-qubit. Now suppose we have a whole system of interest, which is n-qubit. Descriptors are generating sets of operators. In this case, what we can take for a generating set of our operators acting on the Hilbert space of n qubits is gonna be these two n operators. Sigma x tensor identity elsewhere, sigma z tensor identity elsewhere. These are the x and z component of the first descriptor, or the descriptor of qubit 1. I bundle these two objects together into a pair, and that's why it becomes bold font, and it's Q1 of 0. The sub 1 refers to the first qubit. Now, these two operators are bundled into Q2 of 0, and so on, until we get to these two operators here, Qn of 0. Right? And okay, and then if we can speak of the total descriptor or the whole descriptor of the system as merely the collection of local descriptors, Q1 of t, Q2 of t, until Qn of t. So it's an n tuple, each object is a pair of operators. But why does it work? Why is it a generating set? Because by multiplying these operators together, we can get to that basis, where sigma mu runs from 0, x, y, z, and sigma 0 is the identity operator. Right? So by clever multiplication of these two n operators, we can get to any of these 4 to the n basis operator. And since we generate multiplicatively a basis of linear operators, then by addition or linear combination, we can get to any matrix in the total Hilbert space, right? Which is 2 to the n dimensional.
Oh, there's a question.
Yes.
Do we know what is the minimum number of generating sets in this case?
Yes. The minimal number of operators in my generating set, I guess you mean?
Yeah, no, the optimal way to choose our generating set.
Yes, okay, yeah, exactly. You can boil it down to 1 per qubit. So one way to see this is to consider the following object, sigma x plus I sigma z. If I would do that, I would have taking the real part of this expression would give me how the sigma x evolves in time, and taking the imaginary part will give me how the z evolves in time. That's one way to see it. Or if you like, another way to see it is that sigma x plus I sigma z in fact corresponds to this matrix that has a 1 in an off-diagonal term and zeros elsewhere.
But do we know the optimal answer?
Pardon me?
Do we know the optimal answer to that?
The optimal answer?
The optimal number of generating sets.
Yeah. Well, then I've reduced to 1 per system. So that would be the most economical we can get. If we assume that the total Hilbert space has this decomposition into subsystems, which we usually do in quantum computation, right? In quantum computation, we're not given a 2 to the n dimensional Hilbert space without structure. That's not the deal. The deal is, yes, we have a 2 to the n dimensional Hilbert space, but moreover, physically speaking, that Hilbert space is made of, say, n spins. And therefore, a more faithful representation of the total Hilbert space is actually C2 tensor C2 tensor C2 tensor C2 n times. And so that matters. Sometimes mathematicians forget these details, but it kind of matters because otherwise, they will tell you, these mathematicians, all 2 to the n dimensional Hilbert spaces are isomorphic. And then you kind of lose the physical connection to a system which is made of n spins. I mentioned this because it matters in our context. I'm assuming here that we have n systems. And so I'm going to be interested in 1 descriptor per system if I want to be minimal. The trick is I don't really mind being minimal. What I want is to be efficient for calculations. And therefore, I'm going to track 2 operators because it's easier to track in time these Pauli operators than to track in time this minimal operator, which is, as I said, a combination of the Pauli operators. Yet, like if there wouldn't be this decomposition of my whole system into n subsystems, I could even go and say, oh, there's one generator for the whole 2 to the n dimensional Hilbert space. Yet I push back against that because it doesn't reflect the physics of the decomposition of this 2 to the n dimensional Hilbert space into tensor products. So yeah, the minimal thing we could do here would be 1 per system, but let's do 2. As I say, it's more efficient for calculations. Okay. Okay, same as before, if we have time 0 and time t, the descriptor of qubit I, like some generic qubit I, at time t will be given by this equation. And if it happens that, in fact, between time 0 and time t minus 1, like before, we have a gate V, and then between time t minus 1 and time t, we have a gate W, well, then I can also invoke this step-by-step equation of motion, right, which relates the descriptor of qubit I at time t in terms of the descriptors at time t minus 1. So note that now what I'm evolving in time by conjugation is qi of t minus 1, right? The descriptor of qubit I at time t minus 1. But I'm going to be sandwiching it with the functional representation of the gate W, which will depend on, here I've put Q without any label, which in a way could be thought of the whole collection of the descriptors. Prima facie, let's consider that it will, in general, depend on all the descriptor components if I have no assumptions on W. But if W is a gate that affects, say, just qubit J, or perhaps if you want qubit J and qubit K, well, then the functional representation of W will depend only on Qj and Qk if it acts on 2 qubits. If it acts only on J, like what I'm claiming here in my slide, in fact, it's only Qj that I'm putting here. Okay. That's important because we'll realize that if I is not J, okay, I is some other random qubit here, like below, then we're doing a gate on J. We would like the descriptor of qubit I to be left unchanged. That's one of the promise I made at the beginning of this talk, saying like, if we apply a gate on some other system, the descriptor of qubit I will be left unchanged. And we'll consider this here. Now, the other algebraic relation of descriptors I'll make use of now that we have multiple qubits, you know, like my algebra is no longer the Pauli algebra of a single system, it's kind of the Pauli algebra of multiple qubits. Importantly, we find this relation that Qi commutes with Qj. And here I'm kind of abusing the notation by keeping the bold fonts. But what it means is that they each component commutes with each other component. QiW, W is some component, either X or Z or Y. It commutes with QJW prime. W prime is either X, Y, or Z. And also that is going to be preserved in time, and therefore these commutation relations are also true for generic times. Therefore, also in the assumption where J is different than I, and therefore W is a gate that is not acting on I, this expression here, UW dagger of Qj, will contain algebraically many terms of J-like term, you know, it will depend on Qj's components. And therefore, it will commute with the descriptor at time t minus 1 of qubit I. And this will meet this, and it will cancel out into the identity. Okay, so this was a sanity check that what I promised that the Deutsch Hayden descriptors are local in the sense of Einstein, well, they really are. They have the same property that reduced density matrix have, which is if Bob plays with his system, it will not affect the reduced density matrix of Alice, right? Now, if Bob is playing with qubit J, it will affect the descriptor of qubit J. The gate W will act non-trivially on the qubit J, but it does not have an effect on qubit I. And we can see it from this step-by-step equation. Okay, so if we want to get concrete a bit more with this framework, we've got to find the repertoire of the various actions that the gate have on the descriptors. We found it for the Hadamard gate. We've studied the Hadamard gate, right? And we found that whatever descriptor enters at time t, you take its components and you swap them. So that's the action of the Hadamard gate on the descriptor. What's the action of a NOT gate, an X gate on a descriptor? We solved the problem, right? We have to write down X as a matrix like that and find the functional representation. Namely, we have to find how, with the algebra of descriptors, can we generate that matrix, and that's the solution. And therefore, Ux of Q is Qx. It's just Qx. And therefore, if I want to compute my descriptor at time t plus 1, and given that my descriptor at time t is given by this expression, I'm using the step-by-step equation, and I find that, well, the functional representation of the gate X is simply Qx here of t, so I keep the of t, and I put these inside each term, and I use the algebra of descriptors at time t, but it's the same as at time t, at time 0. Therefore, 2 of the x component cancel out. I'm left with 1 x component here. Here I use the anti-commutation relation, and I find minus qz of t. Therefore, a gate X is such that if a descriptor enters, we leave its first component or its X component unchanged, but the Z component finds a minus sign. A C0 is interesting. Obviously, we have to work out the C0. The C0 is a bit more work, right? Because we're going to have a 2x2 matrix, which we're going to have to express in terms of the algebra of descriptors of the qubit 1 and the qubit 2. So we have to find how to generate that 2x2 matrix with Q1x, Q1z, Q2x, and Q2z. And then we do this trick of using the algebraic relations to find, what's the functionality, what's the action of the gate, and we find the solution. So check my paper if you want to see the calculations, or better do it yourself. It's not so hard at the end of the day. But what we find is that if we have Q1x and Q1z as an initial descriptor of qubit 1, which will be my control qubit, Q2x, Q2z, which will be my target qubit, well, the Q2x goes upstairs with the Q1x, and the Q1z goes downstairs with the Q2z. That's what a C0 does. Here, I'm sorry, I'm only claiming it. I'm not proving it like we've proven it for the Hadamard and the X gate, but I'm sure you understand that it would just be just work.
I have a basic question. So
Yes.
with the C0 and the Schrodinger picture, the X, or it does a bit flip on the second bit, right? Based on the value of the first bit. And so I guess I would have thought that would be reflected in the descriptors, that Q2 would have gotten the Q1 of X rather than the other way around. There's some intuition for what's going on?
Right. So if you are to encode just a classical bit into a qubit, right? In the Schrödinger picture, you'd have either ket 0 or ket 1. That would be your encoding of your bit.
Yeah.
In the Heisenberg picture, what you can think of is, so importantly,
Oh, it's the observable. Okay.
never mess with the Heisenberg state. The Heisenberg state is always ket 0. We never play with it. It's much better to understand the framework this way. So if I'm feeded only ket zeros and I want to encode a classical bit, namely either a ket 0 or a ket 1 in the Schrödinger picture, what I need to do is take my initial system and either apply a NOT gate or not apply a NOT gate, like leave it as is. All right. And the impact that it will have, it will either toggle my Z component with a factor of -1 if I do apply the NOT gate, or it will not toggle it. Therefore, a classical bit that is encoded into a descriptor has the following form. It's QX, comma, plus or -1 QZ. And the bit is encoded in the either plus or minus QZ. Okay, so all this to say that then you can reinterpret the C0 this way, right? If I have 0, 0, like my top wire is encoding a classical 0, obviously in a descriptor, my bottom wire is encoding a ket 0, then I have plus QZ plus Q2Z, and I have plus, which is also 0. If I have 1 on the top qubit and 0 on the bottom qubit, I have a -1 here. That -1 will carry through here. And so the bottom qubit will become a 1. And so you do find the algebraic properties of the classical C0, if you like, but you must read them from the sign of the Z operator here, if that makes sense.
Thanks.
Okay.
So another question is, so far, it's all Clifford gates, and you can track everything efficiently. You know, you were commenting earlier about efficiency, but then presumably, if you want to do this kind of thing with T gates, it gets a little more involved.
Yes, yes, nice comment. So, but by the way, I think with my presentation, in case you're interested in the Gottesman 1998 paper and eventually the Gottesman-Nil theorem, maybe things will be a bit more clear. Now, Gottesman did not, he finds out about descriptors in the first part of his paper. Eventually, he gets into stabilizers, which is kind of a close cousin of descriptors. But it's definitely related to the descriptor framework. And in this slide, we can understand the Gottesman-Nil theorem quite with some light, right? So as you mentioned, Mark, if I keep H and X and Clifford gates, C0, and I were to calculate the descriptors on each qubit that are evolving in time by Clifford gates, my calculation will always be easy, right? A Hadamard gate, switch the component. A X gate, just put a minus here. Obviously, you'll figure out if it's a Z gate, put the minus here instead. A C0, okay, that's a little more convoluted, but really not really, right? You just write Q2X here, you copy stuff. And so it could be efficiently classically simulated. Now, what's the deal with a T gate? The T gate will do this annoying thing, which in one descriptor slot, you'll have two terms appearing. And then if you start putting more and more T gates, you start to branch the number of terms within each slot of your descriptors. And
Sorry, can you repeat this last part? So with the T gate, do you have addition? Is that it?
yeah, you'll have addition within a slot. You have something like Q1Z with some coefficient plus Q1X of something with some coefficient.
And so that'll lead, as you have more T gates, you'll have like a blow up in
Yes.
It'll be hard to describe efficiently.
Correct.
Okay.
Yes.
Thanks.
Nice. Pleasure. Okay, so that was my goal for today. Give you a crash course on Deutsch Hayden descriptors. Maybe I should just mention that, as I said, descriptors also solve some problems in the locality aspect of quantum
Yeah.
protocols. That if we do in the Schrödinger picture without this factorizable framework, it seems like there's action at a distance, or it seems like we cannot explain Bell correlations and so on. And but yeah, for me, it was the best selling point of this framework is that if we take it seriously, we have a solution to the problem of teleportation, superdense coding, Bell. And there's also interesting remarks to make about the relationship with causal models, like notably the recent advance in quantum causal modeling. I'll do superdense coding.
Is that French?
Yes, I realize it. Yeah, I gave this talk in French once.
Sure.
So that's superdense coding. Alice and Bob are sharing a phi plus, and the general way in which superdense coding is presented is that with this shared resource, Alice can send 2 bits of classical information by sending only 1 qubit. So she has 2 classical bits that she'd like to communicate to Bob, and she'll encode them in some operation that depends on I and J. Local operation that she'll be performing on her qubit, right? And in the Schrödinger picture, what it says is that depending on which operation she performs, she's transforming the global state into one of the 4 Bell state. So I wrote here Bell sub ij, right? The Bell state is labeled by I and J. Then she transmits the system to Bob. Bob performs a Bell measurement, retrieves ij. Okay, I guess obviously, if you guys are trained into computing very hard stuff, because I know Mark's book is hard, like there's a lot of elaborated calculations to do in quantum information. And you know, sometimes if that's our expertise, we're not so much into the philosophy of physics kind of framework where we wonder, but what about the state of the universe, right? But suppose we address these questions just for a little bit. Like what's happening in the Schrödinger picture in superdense coding? By performing one of 4 operation, Alice is altering the whole state into one of 4 states, and then she sends that to Bob, and Bob can retrieve it. But I guess my question for you is, where physically do I and J reside after Alice has performed her operation? And okay, we might resist the temptation to say, oh, it's like a channel, it's the I and J right away jumped on Bob's side, but it's still, in the absence of this local and complete framework that I'm advocating for, it seems like it's residing into holistic properties of the entangled state, right? And some people make peace with it. Oh yeah, entangled states have holistic properties. You can encode the operation ij into the correlation of the Bell state and so on. Definitely the operation ij is not even retrievable from the local density matrix of Alice alone. So it really has to be somewhere in the global state that it's not in the density matrix of Alice alone. So where is I and J? That's my problem. And let's investigate that with descriptors. That's the protocol for superdense coding. Like as I said, we don't mess with the Heisenberg state. It's always get 0. And so if we start with a phi plus, we need to prepare it explicitly. And that's what we'll do. We prepare the phi plus, we apply the operation that depends on I and J, so it's X and Z, and Bob does the Bell measurement. Let's compute what happens to descriptors. Q1X, Q1Z, right? Here, when there's no time label, it's like the initial representation of my descriptors in terms of the Pauli matrices. Q2X, Q2Z on the second wire. Now we do Hadamard. We found that before. We need to switch the descriptor components. Then we do a CNOT. The C naught gets the Q2X to go upstairs here alongside the Q1Z. And the Z component, which is now Q1X, goes downstairs alongside Q2Z. Okay. Note that descriptors are such a local formalism that we can safely perform the computations on the wires. That's amazing. In the Schrödinger picture, you can do it so long as you don't have entanglement. But when you have entanglement, forget it. You cannot write down on the wires what's the state of the system, right? You have to take an extra piece of paper and write it somewhere else. Now here I can just use my network to write down my descriptors. And they evolve. Whenever they meet a gate, they will evolve with respect to that gate. So that's now x to the power of j, right? If j is 0, it just means the identity. If j is 1, it means I'm performing the gate x. We've seen what the gate x does. It does a -1. So it turns out that this expression works for both cases. If j is 0, I have nothing done, basically. If j is 1, I've put the minus sign here. Now I do z to the power of I, same thing, but I'm putting a -1 on the x component of the descriptor, if the bit is 1. So you see, like if we're taking descriptors as a description of physical systems, nothing was done on Bob's side. Alice has managed to stuff 2 bits into her descriptor. Like, yeah, guess what? There's a slot for a bit here and another slot for a bit here. Now she's going to send that to Bob. Bob also has, in memory his entangled state. He's going to perform the Bell measurement. Well, let's first check the Bell transformation back. It looks like I haven't computed all the way down. I should have done so. Let's do it together, right? So this one needs to go downstairs. The Z component needs to go downstairs alongside here, this one. Okay, so I would have -1 to the power of j, Q1x, Q1x, Q2z. The two Q1x's cancel. I'm left with -1 to the power of j, Q2z. So that is correct. And now the x component here in the target of the C naught is unchanged. So Q2x remains Q2x. Cool, we've verified this. Now, what's happening here, where my mouse is that this operator here goes upstairs, right? It goes upstairs, it meets another Q2x. That's nice because Q2x, Q2x cancel out. And so here I have -1 to the power of I, Q1z, comma, -1 to the power of j, Q1x. And after the Hadamard, I've switched the component. So the -1 to the power of j, Q1x goes here, -1 to the power of I, Q1z goes here. Okay, I've just verified that this is correct. And now what Bob has? He has -1 to the power of I, Q1z, right? Which is this operator here. The bit is encoded on his first qubit. The bit I is encoded on his first qubit, and the bit j is encoded on his second qubit. So we could compute like what happened if we do a measurement like we've done in the first example with the Hadamard gate and the measurement, and we would obtain that he measures with probability 1 ij. Okay, so obviously it gives the same distribution that we would get in the Schrödinger picture, but the story is different. The story told is very different. Because we see that everything is completely locally happening on Alice's side.
I have a question.
Yes.
It somehow would feel cleaner if on the descriptor at the last step, in the first qubit, the -1 to the j were not present.
I see.
Right? It would feel very clean if we had that not there and just -1 to the I and -1 to the j. Then based on what you were saying earlier, it would be very clear that when we measure, we would get I from the first qubit and j from the second qubit. Do you have any comments about that? Is this related to like a global phase or something like that?
Yes, okay. So nice question. You if you would try to measure J from the first qubit alone, you would systematically fail.
Okay.
The easy, cheap answer is that we know that operationally speaking or instrumentally speaking, the predictions in the Heisenberg picture are the same as the prediction in the Schrödinger picture. And the Schrödinger picture predicts that only ket I will be measured here. There's no information whatsoever to retrieve about J. That's the cheap answer. The nicer answer is work the math and try to work which measurement or which observable you can come up with on this descriptor. And you'll find out that once you compute the bracket with the Heisenberg state, because the initial Heisenberg state is an eigenstate of Q1z and not an eigenstate of Q1x, this Q1x will be eternally annoying in your trying to measure J, because it will always give you random noise when you try to measure J. Whereas this one is kind of initially prepared. It's an eigen, I like to say it's an eigen operator of the Heisenberg state, right? The Heisenberg state is an eigenstate of this, and therefore I is readable, but J is not. So yes, but maybe like a second comment is you'll find out in the descriptor formalism that we have some of these asymmetries coming up. For example, the phi plus state was supersymmetric in the Schrödinger picture, right? 1 over root 2, 0, 0 plus 1 over root 2, 1, 1. However, here, it's no longer as symmetric, right? It seems like we have a Q2x here. Okay, that's fine. That's his own Q2x. But now this one no longer even has a Q1x, his own Q1x. It's now a Q2x also in a Q1z. So we break the symmetries in many ways. And that is related to the fact that mathematically speaking, there's many different sets of descriptors that surject onto the same Schrödinger state. And this was known from the 2000s, like the work of Timpson and Wallace and Timpson. They realized, hang on, Deutsch Hayden framework is not exactly in one-to-one map with the Schrödinger framework. By one-to-one, I mean, it would be one-to-one if you given a Schrödinger state psi of t, you can compute unambiguously a descriptor q of t and vice versa. But that's not the case now. If you have a descriptor q of t alongside with its fixed Heisenberg state, which I assume you know, then you can compute unambiguously psi of t, the Schrödinger state, but not vice versa. There are many descriptors corresponding to the same psi of t. There's a surjection. That, by the way, is a topic of a paper that should be coming up soon. I was invited to write on a book chapter on Everett and locality, edited by Alyssa Ney. It's going to be published in the Oxford University Press. And I wrote a chapter on that aspect, on the fact that there's a many-to-one correspondence between the Heisenberg picture descriptors and the Schrödinger states. And therefore, I use that to question the usual, quote, proofs of equivalence between the two pictures. All right, so basically my claim is the two pictures are indeed equivalent if what you care for your equivalence is an instrumentalist prediction of theories. Like, it will give the same predictions. However, if you're somehow a realist about quantum mechanics, and you say, no, my world is really described by psi of t, or it's really described by q of t, the descriptors, well, then these stories are not isomorphic. And so, yeah, we have this non-equivalence at the realist level of the Heisenberg and Schrödinger pictures.
I have another question. Is there a way you can modify the dense coding protocol just a little bit, such that in the last step, the -1 to the j is gone?
Maybe.
Okay.
Oh yes, I think so. Yes. So my initial intuition was Bob measures here, he gets j. And therefore he can perform z to the power of j. Because z to the power of j will, depending on it will reinsert a -1 to the power of j here.
Mhm.
But then if you don't like the fact that he measures, we could all do that unitarily with like, it would basically amount to doing a control Z from the bottom wire to the top wire, and you'd get rid of the J.
Okay,
If I'm not mistaken, right? If I did,
it sounds reasonable. I
yeah,
think you should proceed because we do have to stop in 15 minutes.
perfect. Yeah, it will be a perfect place to stop. But I'm happy at least we saw one case.
Yeah.
I think the most interesting case is teleportation. So super dense coding, I've never seen written anywhere someone's being extremely serious that, oh, therefore quantum information goes faster than light across entanglement or something like that. However, you do read such comments when you have people studying teleportation, because teleportation is quite surprising in the Schrödinger picture, right? What's the deal in teleportation? You have Alice prepares a qubit in a state alpha 0 plus beta 1. She can write her life in alpha and in beta because these are complex numbers. Like, they have infinite capacity if you want. She could really type her life in LaTeX, export that as a bit string, and put that bit string into alpha. Okay? And now they share an entangled pair, phi plus. Alice will do a Bell measurement. She takes a telephone, classical communication line, and she sends I and J to Bob. Bob applies a quantum operation that depends on I and J, and he retrieves alpha and beta. He retrieves Alice's life, that is really sitting here in his hand. Now I hear you. Yeah, of course, he cannot measure alpha directly. Yet, again, if I defend this idea that we should try to explain the world in physics, like if really psi is telling us some description of the world, how is that description depending on alpha? We have a capacity problem. There was only space for 2 bits to be communicated. Yet somehow alpha made its way. And so the problem of teleportation is, how do alpha and beta make their way from Alice to Bob? Right? And it feels like it's teleported. By the way, many people have put forth tentative explanations, right? Like Josa said, it goes right away across entanglement instantaneously. Penrose has advocated for it goes backwards in time. Alpha goes backwards in time to the creation of the entanglement space-time point, and then back forth in time again.
Josa actually said something similar in like a 2001 paper, I think.
Oh, okay. Yeah, okay. I can imagine that these two tales are kind of related, right? Because if you're serious about the bridge, about this being a bridge, well, then its causal path, I mean, its causal diagram is a V shape in space-time, and so it's kind of related. Okay, so here's a talk in which I explain the Deutsch Hayden account of teleportation. It has been now turned into a paper titled Teleportation Revealed. And just for the story, but when I was studying this, my PhD advisor was Gilles Brassard, one of the co-inventor of teleportation. And I was so excited one day when I finally understand enough of Deutsch Hayden to carry on the calculation of teleportation to Gilles, right? We booked a whole afternoon. I showed it from the beginning to the end, how the teleportation protocol works and in the Heisenberg picture. And he right away recognized it's the most satisfactory explanation of teleportation. So at least I've convinced one person. Please don't take this as any authority that it should convince you, but you can make your own mind. Right, so I could eventually present how it works, but I would need more time, obviously. Maybe one other aspect which I find very interesting is the local account of Bell violations. Bell violations seem or is declared by many as a proof of non-locality of the universe. It turns out that if we take the Heisenberg picture descriptors seriously as a physical description of systems, including measurement apparatus. Measurement apparatus is also a bunch of electrons and photons and matter, which, insofar as we know, is best described quantum mechanically. This leads to Everett's unavoidable idea that, well, also observers that are also made of electrons and atoms and so on, in a very large Hilbert space, sure, but still they also become entangled with the measurement apparatus and therefore split. Now, if you look at that story, but in the local account of Deutsch and Hayden, the split is purely local. And that purely local split, where Alice measures and Bob measure, importantly in the Bell violation, is not the end of the story, right? Because Bell violations, well, Bell inequalities are not violated at space-like separation. They would amount to being violated at space-like separation if we adopt a single world orthodoxy where Alice has recorded a definite measurement outcome, say 0, and Bob has recorded a definite measurement outcome, say 1. Then if it's definite, even if at space-like separation, joining them together and comparing the list is a trivial operation. However, when we consider everything quantum mechanically, including Alice is a quantum mechanical device, Bob is a quantum mechanical device, well, then their comparison of lists must also be treated quantum mechanically. And here I do it in the Heisenberg picture with descriptors. And what we find is that there's a non-trivial arrangement of the bubbles. Alice who've seen 0 and Bob who've seen 0, even if locally they have a probability measure 1/2, 1/2, when they meet each other to compare notes, quantum mechanically we can model this interaction, and we find that the weights rearrange to get the cos squared pi over 8 divided by 2, where they match with 0, 0, and cos squared pi over 8 divided by 2, where they match with 1, 1. And the violations of Bell inequalities occur in the future light cone. So this is about to be published now in the Proceedings of the Royal Society. It's I'm at proofreading stage, so it should be up in the next week or so. I can follow up with the papers if you're interested. I would also be, happy to discuss it with you guys if there's any interest.
Yeah, that sounds very interesting, and congratulations.
Thank you. So I finished with a quote by Dirac. The Heisenberg picture is a good picture. The Schrödinger picture is a bad picture. And the two pictures are not equivalent. So I'm kind of cheating here because Dirac didn't say that in the same intention that I had with this descriptor formalism and the non-isomorphism between descriptor at time t and state at time t. He said that because in quantum electrodynamics, sometimes you have no solutions in the Schrödinger picture because you have divergences to keep track of. But still, it is in a way, it has become my position, these precise words, regardless of the intent of Dirac.
It's funny because Dirac was the one who unified the Schrödinger and Heisenberg pictures, right?
Indeed, yes. And
years later, to see this is the quote that you don't see, right? Like,
yes, so it's an interesting story. I guess I should maybe dive more into it, but his first edition of his book was done completely in the Heisenberg picture. And then he was convinced that they were equivalent, so he rewrote the book, I think from the second edition or the third. It's all of a sudden, it's all in the Schrödinger picture. And later in his life, he mentioned that he realized that that was a mistake, that the pictures are not exactly equivalent. You can find some of his papers, like Quantum Electrodynamics Without Deadwood, 65 is one of them, where I believe I've quoted from that paper. Yeah,
it's
so
very interesting because his book, being in the Schrödinger picture, I think had a huge influence on how people think and do calculations with quantum mechanics, right?
Mm-hmm. Mm-hmm.
Had
It does.
been in the Heisenberg picture, maybe we would be teaching quantum mechanics and quantum information differently.
I believe so, right? I believe so. It's definitely like a different gymnastics when we do the calculation the Deutsch Hayden way, and it's as I say, it's a different story. I happen to care about stories when we investigate quantum protocols. I'm one of those, like how does it work? Why does it work? And I respect that it's not for everyone, right? So some people are, they prefer dedicate big mathematical machinery to perhaps discover new protocols or new cases. But I'm of the opinion that if we want to make fundamental progress, sometimes changing our lens to a story in which things are clearer, or I would think are clearer, then maybe we should take that seriously. So, for example, I'm curious to investigate how quantum algorithms work in the Heisenberg picture, right? Because if the story is very different, it's not only different for these locality questions, it's different period. So what's the story like of the Grover algorithm in the Heisenberg picture? Or sure, um, uh, these are some of the questions that I've been starting to ask myself. I'd be happy to discuss, guys. I've been talking for a long time. If you guys have comments, questions, or any sort of criticism, I'm also obviously very open to.
So it's very interesting. Thanks a lot for the talk. I do have two things I thought of while you were presenting, and one of them I think I mentioned when we were chatting in Montreal. People, especially a collaborator of ours, Zoe Holmes in Switzerland, have been pursuing the Pauli propagation method for classical simulations of quantum algorithms. And it seems like there's overlap, at least in a technical sense, between what you're doing and with what they're doing. And I don't know that method so well, what they're doing. I mean, she presented our group meeting previously about this when she visited. But this insight that you had about the functional representation of a quantum gate, I don't recall that being part of that method. And that seems extremely valuable because it allows you to sort of, eliminate gates that are not acting on certain qubits in the descriptors, right? And so anyway, so the comment is just generally like, the question is, could this be useful in understanding classical simulation of quantum systems?
Yes, I see. I do think so. It seems clear to me that that's how Gottesman arrived at his theorem. It was in the Heisenberg picture.
Right. But extending that more generally, like if you have
Yes.
just a few T gates, then you can track everything with these descriptors, right? And there's not so much overhead.
Yes.
As you add more and more, it gets, the descriptors get exponentially complex, right?
Correct. Yeah. Maybe we could also find, within the algebra of descriptors and of the T gates, is there any simplifications, that we could eventually find, like if this number of T gates is performed, but in this way, it turns out the descriptor components cancel out in such a way and things become manageable. I'm speculating here, but yes, all that to say, it's a promising framework to study this.
Yeah, then the next comment is, it's more of a comment. It could be interpreted as a criticism, but in quantum information, one of the core quantities that we deal with is what we call divergence, right? Or like relative entropy, which measures distinguishability of two quantum states, right? And that's fundamentally a Schrodinger picture object, right? Maybe there's a way to think of it in terms of descriptors. And from relative entropy, we build up like everything. We build up, we get entropy, we get conditional entropy, we get mutual information, and then it allows us to quantify how much of something we can do or how much of something we have, right? And so when we go to descriptors, there's a feeling like we lose that, right? And so that would be somehow problematic, but maybe there's a way to reformulate things like relative entropy measures in the language of descriptors. And so that's a general comment, and then it leads to a question, like suppose that I wanted to calculate entanglement using descriptors. Have you thought about that?
Yeah, very, very nice comments. So I'm not sure. Well, I guess I've showed it in my initial slides, right? Where I flashed that from QA and QB, we can compute row AB, the density matrix of the whole. And in particular from from QA alone, we can also compute row A, right?
Yeah.
So if it's a matter of not having lost the mathematical ingredients to make sure we can still compute divergences or von Neumann entropies, well, then they're still there. These ingredients are still there because you have QA, you can compute row A, you can compute row B from QB, you can compute the divergence of the two density matrix or relative entropies, and so on. So mathematically speaking, it's not lost. Now I'll give you the point. It's not in our face anymore as much as it was if what we were actually explicitly tracking in time was the density matrices themselves.
Mhm.
So, but I think that opens the door to some new explanations about, okay, but then what is entropy in the quantum setting, right? Okay, how can it be articulated maybe from first principles in the descriptor framework? I have two colleagues who are working on that at the moment, or these kind of questions, Sam Kuipers and Maria Villaris, and
Okay.
and it seems very interesting. Like they they're interested in getting back to von Neumann entropy, I believe, from arguing in the Heisenberg picture. So I think that, but you put your finger on, yes, it is a problem. Like, okay, but then what is that, in the Heisenberg picture? But I think like all good problems, they might be fertile. They might be worth investigating. And they're obviously not unsoluble or.
Yeah. Cool. Do you have any questions? All right. If not, let's thank Charles.
Thank you very much, guys. I was happy to be there with you this morning.
Yeah, that was really great. Thanks a lot. Do you have your slides like on a website or anything like that?
I can email them to you if you want.
Okay.
You can share with colleagues.
Okay.
I'll
Great.
probably, if it's okay with you, I'll probably put up this talk online. So
Oh,
if you
perfect.
want to send me the recordings,
I'll do that.
it'd be great.
All right, I'll go ahead and stop the recording. Thanks again.